Hello everyone, and thanks for joining today's Code Along. We'll kick off today's session in about 3 minutes. We're just waiting so everyone has a chance to join. In the meanwhile, we'd love to hear where you're joining, so please ping us in the chat. For this Code Along, you can check out the resources doc, and please note that this session is being recorded, and the recording will be sent to everyone that has registered for the event. So if you haven't already, you can go ahead and register so we can send the recording and resources to you. Hi everyone, thanks for joining today's Code Along. We'll kick off today's session in about a minute. We're just waiting so everyone has a chance to join. In the meantime, we'll love to hear from you, so please let us know in the comments where you're joining from. For this Code Along, you can check out the resources doc, and please note that this session is being recorded, and that recording will be sent to everyone that has registered to the event. So if you haven't already, you can go ahead and do it. And that's everything from me. Now I'll hand you over to your host for today's event, Richie. Richie, please take it away.
Hi there, data scamps and data champs. This is Richie. Welcome to a very exciting Code Along. Actually, before we get started, Reese is on vacation, so I was hoping to retain control or gain control of the warm music, but Ignacio's taken over, unfortunately. So yeah, that was the chill music. I'm not, with all the talk of AI getting better at generating stuff, I'm not convinced the AI music's getting any better. Anyway, moving on from music, today we're talking about sports because, of course, Sunday sees the final of one of the biggest sporting competitions in the world. It is time for another Super Bowl analytics Code Along. So I feel like sports make brilliant subjects for analytics in general. American football in particular is especially data heavy. So there's a lot of exciting stuff you can do. And so in preparation for Sunday's face-off between the Patriots and the Seahawks, we're going to look at using data to predict the winners. Now, our guest is Will Bracken. He is a data science manager at MongoDB. Hi, Will. Welcome.
Howdy, Richie. Thanks for having me.
Great to have you. So before I introduce you further, I think just to make sure there's no bias in today's analysis, do you have a favorite between the Patriots or the Seahawks or any other teams you're a fan of?
I will say that as a fan of the Tampa Bay Buccaneers for a long time, I don't have any skin in this game, but I am very interested to see where this Super Bowl takes us.
Absolutely. As good to know, there's no bias creeping in there into the analytics. All right. So Will runs the data team supporting sales and go-to-market operations at MongoDB. He's got a decade of experience as a data scientist with stints at PwC and AIB. So slight different field of analytics today, but yeah, I'm looking forward to it. Please take it away, Will.
Thank you very much. So yeah, a little bit about myself, as Richie mentioned, spent the past decade or more helping organizations make good data-driven decisions. Building models is just a nice way for us to help kind of simplify the world around us. In my professional experience, that's financial models and business strategy, but we're here for the NFL and the absolute love of the game. So as an expat living in Ireland, it's been a privilege to kind of watch Ireland as a country grow into this sport that's now global and all over the world. So without further ado, I'd love to be able to talk to you guys and bring you through on this journey to predict the Super Bowl ahead. So I'm going to go ahead and share my screen to get us started here. And while that's coming up, we are going to take a quick look at the data available to us here. We'll be touching on the NFL Verse data sets. This is a community-led data initiative by a great group of folks that are helping to make this accessible and something that we can all benefit and learn from, along with Madden player ratings. Madden is an absolute stalwart in video game sports. And since 1988, having sold over 150 million copies, it's obviously something that's beloved by folks, not only in the States, but all over the world. So while we definitely want to be able to dive into the Super Bowl itself and the NFL, we're also going to take the opportunity to learn more about Python and the polars package specifically. It's often a case that folks, they hear about polars and they think, I already have pandas. But really, it's a case that you can learn about having another tool in your toolkit where polars can help you to get the data that you need, a scale that pandas can often struggle with, while polars is able to crunch things quickly and then leave you with the opportunity to use pandas to do the final tweaks on whatever it is you're pulling. So without further ado, we can start with setting up our environment. And in this, I'm calling it modules 1 and 2, setting up the environment and ingesting the data. So this will start with us pulling the data in from our packages first. Lots of things here in the requirements text. A lot of bog standard things, but then a lot of fun things like the NFL Pros data, stats model, scikit-learn. And here we'll now bring the packages into our environment with nice little print statements to be able to check that all of our versions play nicely together and that they are loaded. Setting up our project, good engineering practices to just make sure that we can see everything in the environment and that it is going to be able to then play through. So in terms of the modules that we'll be walking through today, we will start with setting up. We'll move into getting a better understanding of the NFL as it's grown over the decades. Is it more of a passing heavy league? This is something that we've heard about, but as data scientists, we don't want to just trust a narrative. We want to be able to all right. Beyond that, we'll be then looking into beyond just the play-by-play data that we have. We'll be wanting to look at the talent of the players themselves. Since stats of play-by-plays tell us what's happened, they don't necessarily tell us differentiations between, let's say, a mediocre quarterback in a great system that's helping to scheme up ways for an offense to exploit a defense. And finally, that brings us to our play-by-play data, all this good stats, the player ratings themselves, which can then help us build a prediction machine to help us get an inkling of who we think might win the Super Bowl. So moving on, ahead of this session, built some custom modules in Python. All this is going to do is help us move more quickly into analyzing the data, but certainly worth, as you're learning more about the language and best practices in engineering, it's a good opportunity to be able to say, building more tools in our toolkit, so to speak. So now speaking first about polars. Polars and pandas, the way they mostly differ is the idea that you are, with polars, going to build a blueprint of the data that you want to pull, and then specifically pulling that into your random access memory, into your RAM, versus pandas is eager to pull all data in, at which point you're going to start manipulating. And that's where the real advantage lies for polars, is the idea that you are only pulling the data once you're making that statement. So in here, I can show a quick example of this scan process. We have a Parquet file that has the play-by-play data for the NFL over the past, let's say 5 years here, but we have 25 years in the slimmed version of the play-by-play that we've pulled in. And polars is then going to allow us to build this statement, which is just the blueprint, and is only executed and loaded now when we ask it to collect. And that's the advantage behind it. So anything else is just scanning and playing around. So in this way, we'll go ahead and load this data. This is just the scanning element. And now we'll go ahead and ask it to collect the schema. One thing that polars does very well, and another key difference from pandas, is that pandas is going to orient on pulling in objects, which can be a mixture of strings and integers, but that can often cause bugs if you're not sure in the declaration phase what type of data you've just pulled in. Polars, on the other hand, enforces that strict data type, and this can save you a lot of time debugging after you've already pulled things in. So here, it allows us to print our columns, print our types, and then only pull in the key columns that we want to be able to understand the types behind. So some of the data that we're looking at right here is things like EPA. This is a big one in the NFL. Expected points advantage. So the idea of EPA is going to help you understand, based on the position that you're in the game, how many more points do we think that this next play can help lead us to? And in now wanting to make the direct comparison of how quickly polars was able to pull this data versus how quickly pandas pulls data, we will do a little bake-off of sorts. So this is a statement to be able to pull in the Parquet file via the pandas route. And so pandas pulling 500,000 odd rows has taken us 0.51 seconds here. In comparing that same statement then for polars, so exact same data running, it took us a fraction of that time due to the fact that pandas grabbed everything versus polars is grabbing just the pieces we need, which is if we're wanting to only look at, let's say, past play types that are not null, and only selecting a subset of fields here rather than all columns involved. The verdict then is that polars was 15 times faster for this activity. And now granted, we're talking about less than a second here for this kind of data, but if we're talking about more than 500 megabytes of data and beyond that scale, this is meaningful time that we get to get back as data scientists to spend more time analyzing the results rather than waiting for the results to show up. And throwing in a couple of extra features, the more features, the better when it comes to building models in order to understand what matters and what doesn't. We can pull in things like the betting lines, the game types to be able to contextualize. Was this a team that the Vegas odds makers thought was a really good team versus a more mediocre team? Or is this a game that wasn't very important to the outcomes of trying to reach the Super Bowl versus playoff games where you lose and you're out, where the stakes are higher and the players are likely to play a little harder as a result. So we now take a chance to load our data here, and we can get a sense of some of the Super Bowls, their past outcomes, and the Super Bowl ahead of us here, where we have the New England Patriots versus the Seattle Seahawks. And as of the time that I pulled this data, the spread line being 4.5 to the Seahawks. that negative referencing that the Seahawks are having the advantage there. The expected points added. Speaking to this again, there's a nice little example that we've shared here in terms of if we're at 1st and 10 and you're on your own 20, historical data will tell you that you have this 0.5 points in this drive on average. And the idea that the next play that you're having is going to influence then the next EPA that you have. So a 30-yard run or a 30-yard run, yes, takes you to 2.5. It adds 2 to your EPA versus the next play drops you back -3 if it's an interception. So assigning these concrete values is something that is tantamount to us being able to have analytics then on how this player contributes to this statistical measure. Moving on, though, we will do a quick data quality check to give us context on how many plays we have at our disposal to be able to build our models. And 1.2 million plays across 25 years, 26 Super Bowls is plenty. That makes us very happy. And I might just pause here, understand if there's any questions in the chat, but if not, I can keep on moving.
We don't have any questions yet, and we're having some struggles with the resources doc with out-of-date links, so not everyone can go along yet. We will get all those links updated to you shortly, so everyone can go along. And if you do have any questions about what's happening, then please do let us know. But in the meantime, I think you can, like for everyone in the audience, if you just watch for now, you can always practice coding along later. All right. So as soon as we get the updated links, we'll send them to you in the chat. For now, Will, I think you can carry on.
Lovely. Thank you, Richie. Okay. So the next module called it the Era of the Quarterback, and it's really about us testing this assertion. Is it a case that the NFL is as much of a passing league, or is this more of a narrative that's caught hold because we tend to pay quarterbacks more and receivers more and things like that? So we don't trust those narratives. We'll prove it with data. And this is where we'll have a chance to, as the references get shared out and made available, the chance to get a bit hands-on. So we'll go ahead and start by loading in our packages, loading in our data, and we can build something live. This is the bread and butters kind of polars pattern in order to be able to build your own lazy frame data set that do downstream manipulation. So what we're going to do here is build the season passing data set. The idea here is I have my play-by-play data set or Parquet file that I'm going to bring into a data set. And this will start by me creating an object, invoking the file itself just by saying pbp. Next, I want to be able to filter to only the pass plays themselves. So I'm going to instantiate polars. I want to pick a column, which is play type. And from there, I just want the pass plays. So stopping here, this is a predicate pushdown, which is polars being able to see this filter, pushing it down to its scanner, that is the query builder, and it will physically skip the rows in the file that aren't passes, which is instantaneous. And as a result, it is bringing in a lot less data, making it faster. Next, let's go ahead and group by season. Standard stuff. And what we want to be able to do is show aggregations. So aggregations are ways that we can do things like sums, means, medians, different ways that we can slice our data in order to be able to understand relationships as we build our models. So here I'll go ahead and grab my column, EPA. Let's go ahead and take the mean. And what I need to do is I need to give this a name. So an alias, which would be EPA per play. Those are all the aggregations I'll do here. The last couple of things I might want to do are sort my data. by the season that it is, and collect. That's my statement to be able to pull that data down. And I'll go ahead and bring that variable in. And voila. So I've made myself a little skinny data frame to be able to say for the 2000 season onward, what was the EPA per play for pass plays? Now it's well enough to just see a bunch of numbers. It's another thing to visualize things, to be able to understand that relationship better. So I'm using Plotly. It's a great little open source tool for being able to kind of pull a visual into Frame, but also to interact with it, to be able to actually look at the data points as we go and very quickly see that relationship that since 2000 onward, we are absolutely seeing greater EPA per pass plays. It's easy enough for us to, let's say, pull run plays in, see if that similar relationship exists. Chances are it does. I know because I did look at this. However, it's not nearly as steep in terms of this trend, which speaks to the fact that offenses have spent a lot more time scheming out ways to attack through the air, since it is a lot more effective at, especially coming from behind, to try and win football games. So that is absolutely neat, an insight there that we can appreciate. If we want to just understand beyond, okay, have we gotten more effective at gaining yards through pass plays and points as a result, but have they actually been exploiting this more? Is it a case that people are trying to pass more as a result of this, or is still the league using runs to balance that passing attack? We can do that same kind of lazy frame data set by bringing in our PPP, filtering, grouping, new aggregation here. So this is now a count of all the plays that we have through the length function compilers. Along with that, we can then sum the number of pass plays to give that relative ratio of pass rate. We sort by season, we collect, and voila, we have our percentages of passes each season, and you can kind of get the sense that it's creeping up. But as always, it's lovely to have a visual as well to give us that same sense of, yes, over time you can see, particularly from 2005 to 2015, peak to trough, that there were more pass plays coming along. So we have proven that the NFL is more of a passing league than it used to be. And this is definitely an insight that we can use for our prediction model for the Super Bowl, in terms of, do we think that the Seahawks or the Patriots are a more effective passing team? With that being one side, we want to also get this external validation of Madden as a proxy for talent and see if that holds. But before we jump, any other questions in the chat or questions from yourself, Richie?
No questions yet. I have to say, all these speed ups from the pollers are quite incredible, because it's a pretty sizable data set. So I'm impressed. Actually, do you have a sense of how much of a benefit you get from pollers versus stock pandas?
I did when I was using the full player-by-player data set. So this is a slimmed down version to make sure that it fits nicely within the data camp environment here for this session. When I was using the full set, so that 1.2 million plays across 370 odd columns. So really chunky 300 megabyte Parquet file, which is a great compressed file type anyways. This was a speed test of about 220 times faster using pollers with that data set than Pandas, which is in this particular instance, it was like 20 seconds saved. But every time you want to play with this data, waiting 20 seconds to see the results is non-negotiable, versus pollers getting it in a second or two is fantastic.
Absolutely. 20-second delays are it's annoying because you can't go off and do something else and then come back. So I love that idea that once you've got a bigger data set that it's not going to fit purely in memory, maybe that's the point. And if you're working with it lots of times, you're loading it over again, that's when you get the real benefit. All right, wonderful. For anyone in the audience, please do ask questions. But for now, we'll continue.
Lovely. Okay. So we have our stats, but now we want to get a better idea of Madden ratings. It's something that I've really appreciated is there are ratings adjusters actually that work on this game even after the game's released each year, to week over week study NFL films, look at other data providers like Next Gen Stats in order to update the over 50 specific attributes per player each week. It's kind of like making sure that this is like a real living roster as the NFL season progresses, which is very cool. The only thing with this data is we might have, in the player-by-player data set, cleaned names like Patrick Mahomes versus Madden has P. Mahomes II. This is going to make things very challenging for joining. And as a result, we need to make sure that we have ways to clean and be able to bring this data together in order to build our models. So that is what we intend to do, and pollers can absolutely help us do this. So if we start with the Madden data that we brought in, this is another thing from a curated open source, which is lovely. We have some samples from the players that were in the previous Super Bowls. We have Patrick Mahomes and Travis Kelce, Chris Jones from, I believe, a couple of years last year. And from years prior, we have Brock Purdy, Christian McCaffrey from the San Francisco 49ers. Position team overalls, good stuff. We'll have our next hand-on point right here. And for this, it's now a case of demonstrating how Pandas likes to do the cleaning of strings, which we'll go ahead and start by building a new data set. So I'm going to use that Madden raw data set that I was looking at before with columns. Now what this is going to allow me to do is take my player name column and start to do different activities to it, as I'd like to call it. So I'll take the string, I'll make everything to uppercase. I will, let's say, take out the things that aren't letters to try and make this a little easier as well. The way I would do that is in the form of regex here, A to Z, with spaces allowed. And if it's not one of those things, take it out. Finally, we can trim white spaces from the end, which can often be a problem. And finally, I'll give this field a new name that I'm creating called name clean. We can go ahead and then let's say print by getting clean, select, and then I'll grab what the name was before and the new clean's name as well. Clean. And we'll just grab the first 10, say. All right, all things going well. Oh, all things not going well. I think I need to do a bit of cleanup here by deleting this dot. And voila. So I've made everything uppercase. We don't actually have the seconds on screen, but those be gone too, and no trailing white spaces. So to this point, it reads like a sentence. And the lovely thing is it runs across all CPUs rather than just bogging down one in particular. So giving that same kind of example there, it's a little easier to see originals versus cleans. Taking out those and making it easy. Okay, in terms of joins, ruthlessly efficient. No index management needed, which is super cool. When ultimately you're just trying to get this data together and get back to the mission of building models and finding relationships. So we'll go ahead and build 2 lazy frames here. First is the QB stats coming from the PBP data set. Next is the Madden data. So we're going to go ahead and use our cleaned data there. So we've got 20 quarterback records, and from our player-by-player data set, we have our other quarterbacks here. So qualified quarterback seasons, 937 quarterbacks over those seasons in terms of them, having at least 200 plays of dropbacks, which sounds fair. To that end, we are now going to do our join. So when it comes to joining, I take my primary table. I'm going to join it to my secondary table based on these keys. So names normalized and the season. And I'm going to do it based on an inner join. So I don't have just a bunch of quarterbacks without Madden stats attached to them. All going well. Here we have our stats data attached to our Madden rating here, which is great. So EPAs per dropbacks going to be our proxy for talent being realized versus the Madden rating being that proxy for talent itself. So moment of truth. Does Madden predict this EPA very well? I see a positive correlation there. And what's really cool is that Polars actually has a correlation function built right into it. So I can check both EPA per dropback and total EPA for those quarterbacks. Total EPA actually being a bit higher there, which is great. Now, visualizing the relationship, picture's worth 1,000 words. Here we have our Super Bowl winning quarterbacks versus their real performance over time. And that trend holds up. Interestingly, we can see that in some of the Super Bowls, let's say our dear Peyton Manning here, did not have a great Super Bowl. And we have the opposite end of things where some quarterbacks that had lower ratings, let's say, had excellent performances. So overall, we can see that there is these positive correlations and that EA Sports Ratings adjusters do know what they're doing, giving us validation that we can use this as a feature in our predictive models. And that, kind of helps set the stage for the next step of, okay, so we have stats, we have talent, we can bring this together to build our model. But before we go any further, I'd love to take a pause real quick and check if there's any questions in the chat. Oh, Richie, I think, are you speaking?
Oh, sorry, I do apologize.
There you are.
The audience is very quiet today. We just have one question. I think you mentioned this briefly at the start, but Ryan was asking you about your favorite NFL team.
Absolutely, Tampa Bay Buccaneers. In fact, throw up the little guy. He has a Tom Brady jersey just as well as I do, and boy, that was a great year.
Nice, yeah, very cool. Yeah. That's a cute picture. Okay, so I guess I have a small question for you. Just around, what are the kinds of analytics you think are most important for football? Because it seems like there's a bit of a range, like we've done a lot of data manipulation, but it seems you get like kind of arbitrarily complicated with these sort of things. Do you have a sense of like what is most important here?
Ultimately, I think combinatorial factors. Not to try and go too deep into really complicated sides of things, but being able to build relationships on top of each other tends to be the most illuminating. So if I was to take an example, it's using EPA, which is in of itself a statistic, and on top of that saying, how often is it that we see 20+ yard runs coming from an EPA as like a explosive rate. If teams have more explosive plays, it probably means they're a more dangerous team and a harder one to beat as a result. So building features is ultimately going to be the most important thing that a data scientist can do. Well, building models is fun. Building features is necessary at the end of the day.
I love that. Building models is fun. Building features is necessary. That's very true. And it seems like a lot of the trick then, it's the same with a lot of industries, is about having that domain knowledge to be able to ask really insightful questions. And then once you've done that, like figuring out the data part of this, it's like kind of, well, that's maybe the easy part. It's just like figuring out what are you joining the right places in order to get your answer. Okay. There's a question here from Wen saying, I'm a university student from Vietnam doing supply chain forecasting. How does Polars help with this? So it seems like lots of use cases here for supply chain analytics. I don't know if that's your field, but do you want to talk through how you might use?
I would switch gears entirely, but this is actually back to the day job kind of stuff. Where I could see this being helpful is, especially if you're going to be working with, let's say, data that has like lots of warehouses over lots of days, and we're trying to measure day-by-day changes in SKUs being bought and like resupplied and things like that. You're going to be just working with tons and tons of data. Maybe millions of records, and then depending on the number of features that you're building for your forecasting model, in terms of different lags, trying to understand weekly versus annual seasonalities, adding on exogenous factors in terms of like what was the weather like that day. All of this makes for massive data, and to that end, I would see myself as using Polars to do the first step manipulation, at which point I can then pull things into Pandas after that manipulation's happened, only grab the things that I needed, and be able to do the modeling at that point.
Okay, yeah, that seems very true. Is that once you got like lots of products, like fairly fine grained data on like what's happening with each of those products and like stock levels and all this kind of, you kind of with like some pretty sizable data. It's like it's not uncommon to have like hundreds of gigabytes, maybe even terabytes of data, and so at that point, yeah. Pandas is going to fall over for your data manipulations. This is where Polars really comes in handy if you want to be working in Python. All right, wonderful. So I believe we've got one more workbook to go through. I'll let you take it away on that.
I do indeed. Thank you. So the prediction itself. We built our data sets, understanding quarterback efficiencies, and that's our play-by-play data. Player talent, that's for Madden. Now we build our models. Before we do that, though, it's worth taking a step back and appreciating, the people who came before us that helped us build these techniques. And there's a famous statistician that always sticks with me, George Fox from Britain, who imparted with us the quote, "All models are wrong, but some are useful." And that's ultimately what we aim to build, is that models are a simplification of something that can show an expected outcome. So we aim to build something that is useful to be able to point us in the right direction. And we will achieve that today. So first, we're going to go ahead and bring our packages in, as well as loading our data. So there's my data. There's my packages ready to run. We'll start by bringing the schedules in to say, okay, here are the threading lines, the scores from those previous Super Bowls to help serve as my reference data set. So I'm training on 25 previous Super Bowls where I have data. And then from that play-by-play data, I can start to build those really fun features around, the EPA of the defense, the offense, passes, rushes, all that good stuff. We then have Madden features. So which quarterback was rated higher than the other, which team was rated higher than the other, all that kind of fun stuff. And then finally, market features. So who did Vegas think was likely to win the game? What did they think the score of the game was going to be? And implied probabilities of winning that they calculated themselves and share with the market. One more chance for us to get hands-on here. So Polars directly integrates with scikit-learn. Happy days. We don't need to fight with it. The way we can do that is I have my training set here, my training data here, I should say. So I built my features, stored them here, and I am going to segment them between my features that I want to use to predict the model. I'll store with NumPy. Almost there. Sorry, 1 second. Train data. I think I've just forgot this one piece. There we go. So y train data and home win as our target variable. So even though Super Bowls aren't played at either the home or visitor team's actual site, we select Super Bowls from other places. We do go ahead and let's make sure we got this here. Features not defined. And that's because I've called it the wrong thing. So let me get those feature calls. I'll do it. All right, so we built. Okay, so we built our feature set in terms of the what we're going to be using to make predictions. Y is then the field that we're trying to predict, home win. So, somewhat arbitrarily, teams are assigned either the home or away status, and then we're using that as our target variable. In terms of the way I want to build models, I want to start by scaling my features. It's a case that if let's say one of the features is the amount of money that's being bet on one side or the other, that could be billions of dollars on something like the Super Bowl, versus the EPA statistics that can be, let's say between -1 and 1. Those features can drown each other out. So scaling them then brings them into the same scale of, like a 0 to 1 feature space, in order for us to then be able to compare, apples to apples then based on their size. Also, I love being able to train multiple models at the same time. It doesn't often take too much longer depending on the scale of data that you're using. Best to start simple and build up in complexity as long as the value is there in terms of being able to articulate the loss in explainability to a certain extent, but the uplift in accuracy then can help make that justification worthwhile. We will do leave one out sampling in order to be able to demonstrate predictivity, and we train. So we get our accuracy statistics. We can go into a very deep science behind that, but we'll keep it high level for now. It suggests that at 78%, our gradient boosting model is the best model for us to use for this particular activity of predicting the Super Bowl. Out of curiosity, we generally like to know what's important. Is it a case that we've accidentally introduced a feature that is giving us knowledge that we shouldn't have? If it was a case of, let's say, accidentally introducing a feature that says what was the score at halftime, we couldn't know that going into the game, so we shouldn't have a feature like that going into our model. Along with that, we would love to be able to visualize it, to be able to say what was the most important feature and by how much is that feature more important than others. So we can take our best model, our gradient boosting model that we declared before, and get the feature importance behind that. So generally a SHAP statistic, which is just a way of saying, if we were to use these models to get, or these features together, how much does it contribute, kind of as like an instrument in a concert, is the way I like to look at it. We build a data frame here. It's easy for us to do data frames at this point now that we're dealing with such a smaller scale. And we can visualize it again using Plotly, lovely package that it is. So what does it tell us is most important based on the model that we trained from those previous 25 Super Bowls? It tells me that from the play-by-play data set, that explosive rate and success rate are the most important features there. Those ones being effectively plays that resulted in an EPA increase of 1.5. So that's similar to this idea of like a 20-yard run. It gives momentum to that team that just got that result, versus success rate which is to say, how often did they have a play that resulted in just an increase of the EPA at all? So generally, positive yards would be the indicator there. Interestingly, Vegas themselves have some predictivity in this because they spend a lot of their time trying to measure this as well, and the spread line that they produce, rounding us out there. All right, so we understand our features. We built ourselves a model. Let's see who graciously borrowing the Madden 25 ratings for these two teams. And we can, take a cursory look at the head-to-heads here. So I have the Patriots with Drake May, his Madden overall being 94. The Seahawks, Sam Darnold, his Madden overall is 85. So a slight nod to Drake May there. We are then going to get our EPA stats. So lots of different variants in terms of pass rush, success rate, explosives, all these good items coming into us here. Do another head-to-head. So for the 2025 season, the Patriots, it looks like their EPA is higher than the Seahawks on aggregate. Didn't delve into the success rates and things like that, but that's all going into the soup. Finally, we're going to build our vectors, which is the comparison of these two teams against each other for these statistics, in order for us to finish building our model here. So let me go ahead and run. Features are built. And finally, the moment of truth. We are going to use that to now predict on our live data here from the model that we built earlier. Going to print some stuff. And our prediction is the Seahawks are going to be the winner with 84% confidence, which is pretty good. To that end, I love the idea of like, okay, I have my prediction outcome and things like that, but I want to understand why. So if I was to then jump over to the solution notebooks that we have available to us here, what I like to do with my teams at work is be able to feed the contribution percentages for what resulted in the scores. So for us, the Seahawks scoring 84% on the model, what contributed to that? And so we can pass those contribution percentages into an LLM to explain this to us in natural language, rather than us just trying to look at a bunch of numbers, comparing them like for like with each other, which can often be useful. But let's say we're trying to give this to end users. They often just want to be able to read language and understand the outcome in a way that they would understand. So we have done this separately, but the idea is it's told us that their offense is expected to be more effective at moving the ball, particularly around the success rate EPAs and things like that. Whereas while there was a higher EPA overall for the Patriots, our model was able to find some nuggets that just looking at cursory statistics might not have told us otherwise. So finally, we can finish off with a nice little visualization. Let's give it a gauge. That is our, the Patriots being our home team there, but the nod going to the Seahawks with that outlandish probability. Anyway, that is, us taking ourselves from zero to hero effectively around using polars, using our NFL data in order to build a simple model and kind of dip our toes into the idea of the way data science can help and inform on the world around us. So I'm very happy to dive into any questions or, yeah.
That's very cool stuff. I love that, like you get a concrete, a probability at the end of like who's going to win or not. I don't know whether it's a good idea to actually bet on this based on the probability, but I just did the very simple like Google sanity check, which is just Google what is the probability of the Seahawks winning the 2026 Super Bowl. It seems like the consensus is the Seahawks are the favorites. Most simulations seem to be putting it around 60% chance of winning. I think there's a lot of variability in Super Bowl finals. It always seems like there's some weird upset going on because teams are playing differently because they get nervous or whatever. But yeah, I think it's good that this fairly simple model that we've run just now is giving a sort of a similar answer to like these sort of more sophisticated simulations from betting companies. So that's pretty cool stuff. I'm impressed. Yeah. So Ryan's saying like, are you confident enough in this to bet money on the Seahawks? I say I'm not a gambler. I don't know whether you are. Will.
I'm one for friendly wagers. So generally, it's like if I find somebody who's going to take the other side, put $20 on it, kind of thing. So would I bet the house on it? Absolutely not. Would I put 20 down? Yeah, why not?
Small stakes. Yeah, that sounds like the sensible approach. So I guess yeah, we should probably say please do not bet your entire life savings on the results of today's code along. But I think it's been very good for learning. One thing I'm curious about is, as you were going about building this, did you spot any big differences in how Polars works compared to Pandas in terms of like the syntax for like what you're writing? Like, how is the code different?
Syntactically, yes. Like Pandas is a lot fewer characters, let's say, to try and accomplish the same task. I'm cognizant of that. So it is one of those things of like, I'm not going to switch over entirely one to the other. But the fact that I can work at a bigger scale of data much faster tells me that I really do want to use Polars to take me through those first steps of getting down to the data that I need, at which point Pandas is great for taking over. Pandas is ultimately, there's a much wider community supporting it, and has built in a lot of like flexibility and features into it that Polars hasn't gotten the chance to yet. But that, different tools for different places, I'd say.
Okay, yeah, so I think certainly like if you're doing some fairly standard analysis where it's sort of core tasks and it's big data set, you're going to want Polars. If you're doing something a bit more niche, then Pandas has that kind of wider level of support and for dodgy things that one person wanted to do one time. And so yeah, there's a lot more flexibility going on there. Okay, so with that, we've still got time for some more questions from the audience. Before everyone dives off, I would say please do register for the next Radar conference that we're running on April the 1st. So the Radar series is one of our biggest events of the year. I'm very excited about it. So if Ignacio can post a link in the chat, I think we had one already. So yeah, please do get registered for that. So it's a free event. We've got some of the biggest speakers around talking about how humans and AI need to work together. All right, with that, Will, I very much enjoyed that session. It feels like a good way to build up to Sunday's activities. And of course, playing around with Polars is very cool stuff as well. Excellent. So thank you so much, Will.
Richie, thank you. Thank DataCamp. Yeah, enjoy everyone, and look forward to seeing you next time.
Wonderful. All right, thank you to everyone in the audience. See you again soon. Actually, we've got a big week next week. We're talking about breaking into the AI 1%. We've got some code alongs, we've got some panel interviews, all the usual stuff. So sessions Monday through to Thursday. Please do come back.